circle. Guys, quadrant 2, I think, remind me, I think the ordered pair looked like this. That's true? So if you place y over x there, you place a positive over a negative, which is what? Negative. So here I gotta make sure, since it's negative, this piece, quadrant 2, on the grid, must be below negative. Best I can do here is, just gotta follow the asymptote, not touch, and come up and pick up that x-intercept. That's below. Next, this is quadrant 3. Right here, quadrant 3, I'm gonna get a circle. And I know in quadrant 3, and you know in quadrant 3, the coordinates are these. You place y over x, negative over negative turns into a positive. It says, Professor, when you reach this part here, you better make the graph above. It's positive there, which means I'll pick it up and stay above the x-axis. I do have one more quadrant here. That's quadrant 4 over here. And of course, quadrant 4 had for coordinates. Those, place y over x, you end up with what? Is that a negative? That means I'm below here again, and the graph looks like that. Now, you say, Professor, what am I supposed to remember as a parent graph? Looks like I see quite a few pieces up here. Can you tell me which one you want us to know for the parent? Someone tell me first. Can anyone tell me if I should extend this on out? Anyone tell me what the next point would be after 2 pi if I went further to the right of 2 pi? What do you think the next point would be? What would it look like?
3 pi over 2.
How much?
3 pi over 2.
Not 3.
5 pi.
5 pi over 2. If I should go further, these graphs go forever.
That would be.
Wait, hold on. Would it be 5 pi over 2 the way it's spaced here? Looks like this is 0, 90, 180, 270, 360. It's being spaced by 90 all the way across. Pi over 2. About, if I had 90 here, would that be the next point here? Is that what, 450? Doing in degrees? And I would expect then, Professor, if you ask me to go further and you say the graphs go forever, there's another asymptote here. And I would think then, since we're going to start over, that's like going back into quadrant 1, which is positive, you have another piece that's above here. Now, can someone tell me if I should move to the left? I will do it for a reason. What do you think the point to the left would be if I want to extend my graph to the left?
Negative pi over 2.
Negative pi over 2. We're spacing by pi over 2. What do you think is happening at negative pi over 2?
Happens to
It happens to it. And I bet students in class could say, Professor, if you wanted to, you could now pick up with this and draw a piece like that. Now, could I do this all day?
Yes.
On the right and the left, just draw one cycle after another cycle after another cycle. You say, Professor, please, when you ask me to draw something with a tan in it, you always ask me to put the paragraph. I'll do it through transformations. Which of these should I accept, Professor? For a reason, chapter 6 coming up. We're going to accept this one. It's called between negative pi over 2 and positive pi over 2. The others are beautiful. They would work. If you would use one of these on an exam or a quiz, you say, Professor, I did my graphing, but I used this paragraph. I'll give you credit. I would appreciate, though, if we all are consistent and we use this one for a reason. The guys want to accept my parent graph as this one called between negative pi over 2 and positive pi over 2. With me, guys? Now, let's go through the function now and identify a few things. Period. Let's get the period out of the way. No matter which cycle you look at, period is where it stops and then where it started. Guys, if you do this one right here, it stopped at what, 3 pi over 2? It started at what? Pi over 2. So you know 3 pi over 2, subtract pi over 2 to find that period is what? 2 pi over 2, which is pi. Would that happen also if I tried this one? Pi over 2, subtract a negative pi over 2. Would I end up with pi again? I would. This one, 5 pi over 2, subtract 3 pi over 2. That's what, 2 pi over 2, pi again. So the period for a tangent is pi. It repeats every pi. Amplitude, too bad, there is none. There is no highest point, like I think I had 3 over here on this one. There is no highest point. Don't say infinity. They want a number. There is no number here. Domain, here's where it can get tricky. They want the domain on the entire function, not just on those cycles. You gotta be careful. And I'll get you a little start here. You know, and I know, looking at this, x cannot be certain numbers.
Can you find it?
And you're not gonna have the time to list all of them. I see 3 right now for the entire function. It goes on forever. X cannot be this, asymptote. This, asymptote, asymptote, asymptote. In fact, many students probably could tell me beyond 5 pi over 2, where's my next asymptote?
7 pi over 2.
I think 7, 5 over 2, and then more than likely you can tell me what the next one over here is. That might be -3 pi over 2. Now, can someone give me a good way to express where all those asymptotes are located? Because there's infinite numbers of them, and I cannot list all of them. Matthew, go for it.
So we're saying it can't be pi over 2 or a variation of
Well, yeah, but no, not variation. I know what you're thinking. There is a pi over 2 involved there. Now, I'll give you a hint here. I cannot use, where is it? Pi over 2. I can't use 3 pi over 2. I can't use 5 pi over 2. Some students are telling me the next one would be 7. And more than likely, the next one would be 9. There's a pattern there. What would you like to show someone where all those are located? Jacob?
Pi plus or minus pi over 2.
Oh, you're trying to give me a formula. First, tell me just in words.
Well, it can't be 1 cycle away from pi over 2.
Oh, better than that.
Oh.
And we'll give you a hint again. We've got 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, these are all asymptotes. 9 pi over 2, 11 pi over 2. Now, can you tell someone, just in general, where are they located?
Odd pi.
Odd multiples of pi over 2. So I cannot let x be one of those. An odd multiple of pi over 2. Now, Jacob is doing what I should be doing here soon. He said, Professor, I tried to come up with a formula that would tell you where those asymptotes are without saying odd multiples of pi over 2. He just wants to try to come up with a formula, so hang on to that, Jacob. Okay, domain, guys, range. Range is easy. All real numbers. And I think domain, range, amplitude, none, period, we got that period out of the way. That should be enough to discuss what the tan graph looks like. So right here, guys, is the cycle I want us to know. Even though these others would work as a parent graph. Okay, any concerns here? So we now know what tan looks like. Part B, the last thing I may have a chance here to do shortly here, is this. The one on your handout says something with a cosecant. I'm going to show you what the parent cosecant graph looks like. Here's the last one. I'll probably have only a chance to get this one out of the way. Guys, let me see what this cosecant graph may look like. Now, I've been referring to the unit circle, which is good. Can you tell me one of the graphs we've already done that cosecant is related to? Sine. So what I'm going to do to get the graph on this one, I'm going to graph sine first. I'm not going to go to the unit circle this time. I'm going to graph sine. Squeeze it in over here. Sophia, a little bit warmer now? Okay. Now, here's the parent sine graph. We all know what the sine graph looks like. Sine wave. Looks like this. starts at 0, goes up to 1, back to 0, -1, back to 0. And a wave, something like this. Rough sketch, would you say, guys, that's that what we had for a sine graph? What's the relationship between cosecant and sine? They're reciprocals. Now, can I think in my mind, since they're reciprocals, can I do something with this and get the graph I'm after? Cosecant is equal to 1 over sine. Here goes. They should be reciprocals. My first value on the sine graph is 0. Flip that over, form is reciprocal. Someone tell me what's happening on cosecant. Thank you, it's undefined. I'm gonna start at 0, like 0 over 1. You flip it over, you get 1 over 0. So I'm gonna start the cosecant graph out with an asymptote. Right here. Next point coming up, pi over 2, my sine graph is up at 1, where it should be. That's like 1 over 1. Flip it over, form its reciprocal. What's the reciprocal 1? 1, stays right where it is. No problem. At pi, I'm back at 0. And we said earlier what? 0 has no reciprocal. Okay, so it's going to be undefined again. And we'll have another vertical asymptote. Next point coming up, 3 pi over 2, I'm now at -1. What do you think the reciprocal of -1 is? -1, stays right where it is. Nathan, we're going to finally reach 2 pi, which is back on the axis at 0, and 0 has no reciprocal. Do we end this with another asymptote?
Yep.
How can you go wrong? Now I gotta graph it. Now we have to be careful. Matthew, from here to here is quadrant 1. Please tell the class, we're doing cosecant. What is cosecant at any angle if you're in quadrant 1? Is it positive or negative?
Positive, sir.
Everything's positive in quadrant 1. So that says the first piece of the cosecant graph right here must be where? Above the x-axis. Guys don't have much of a choice. Make sure I get all these colors in here. Let's go back to black. Does that mean, to follow the asymptote, does that mean the first piece may look like that? It's definitely above the x-axis. And it gets close to that asymptote over there, and it picks up my 1. My next interval, Matthew, this is quadrant 2. Please tell the class quadrant 2, if you go back to my unit circle and I place, or we do cosecant 1 over y, what is it in quadrant 2? Negative? It's negative, I'm down below. And when I go down below in this region right here, guys, where am I?
Just avoiding.
Or in quadrant 2, is it positive?
Be positive.
Is it still positive?
Yeah, yeah.
If it is, does that mean it's still above? So it turns and goes back up. By the way, remind me, is cosecant positive in quadrant 2?
Yes.
Yes.
Now quadrant 3, maybe I'm thinking about quadrant 3. Here's quadrant 3. 1 over y, cosecant in quadrant 3 should be negative. This one definitely is below. Stay close to the asymptote, come up. Pick that up. Finally, quadrant 4. Please tell me, cosecant 1 over y, quadrant 4, still negative. That means it just turns, stays below, comes back down toward that asymptote. These two little pieces should be symmetric, they should look alike. But one piece is above, one piece is below. That's one graph, one cycle of the cosecant graph that we gotta know. So I'm gonna accept this as my parent graph. Nathan, here we go. Can you tell the class, be careful, what would you accept the period as? The ending, subtract the beginning. What might the period look like, the period number for cosecant?
Pi.
Okay, tell me again,
Pi.
where's my graph end?
2 pi.
2 pi. Where did it start?
0.
Okay, so that difference is 2 pi.
Oh.
It's the ending of the cycle, subtract the beginning. 2 pi. Now, amplitude, again, sad, there is none. There's no amplitude, there's no highest number, goes on forever, through infinity. Period, amplitude, guys, help me out here, domain. Now, someone's gonna be clever. I see some spots where I cannot let x be something. I cannot let x be 0, pi, 2 pi. Can anyone tell me if you should extend the graph beyond 2 pi, where would the next vertical asymptote show up, do you think? 3 pi. Would it be 3 pi? On the left, would it be what? Negative pi, negative 2 pi, negative 3 pi. Now Sophia saying, Professor, I have a way to express that, to pick up all of them, but you can't list all of them. Tell us again.
No whole number multiple.
A whole number multiple of what? Pi. She said, a whole number multiple of pi. Let's do a little bit better. I see what you're saying. Can anyone do it just a little better, even though I see what she's saying there? Matthew.
No even multiples of pi over 2.
Even multiples of pi, now that's being clever. Even multiples of pi over 2, jeez. You say multiply this by 2, this one by, oh, this one by 2?
Yes.
Pi over 2 times 2 will give me a pi. Oh boy. 3 pi over 2 times 2 would give me 3 pi. That probably would work. I want something else, and you're very close though to what I want. Can anyone tell me what's a good way to express to someone where all those asymptotes are located?
Can it be any number multiplied?
Any number. Now when you say any number, be careful. Fractions like 3/4.
Any integer.
There you want. I want the integers. The domain is any integral, let's use that word, integer, multiple of, I think we said, of what, pi? And by the way, guys, does the set of integers, does that include, please remind me, because I think we saw this set way back somewhere, does that include numbers like these? Yes or no?
Yeah.
Remind me. So Nathan, we're saying if you replace, let pi, put a number with pi from this set down here, you're going to end up with an asymptote. Any number in this set
Yeah.
with pi will give you an asymptote on that graph. Okay. Does that mean, just remind me, does that mean when I get out to 25 pi, if I should go out, all the way out to here, 25 pi, would I expect an asymptote? Yes, as long as that number's inside that set of integers. We'll just call it integral multiple of pi. Woo! How's that look? At least we got the parent graph out of the way. Okay, we've got domain. Did we get range?
No.
Range is too easy. Oh, no, range is not too easy. Anyone describe the up and down on this graph?
Infinity to -1.
Okay, negative infinity, I'll take that. Negative infinity up to, I heard what?
Union 1.
-1 inclusive union
1 to infinity.
1 through infinity. There's your range. Just based on the graph. Now, I don't think, I'm checking my time here. And I realize what the test is all about. We may be here till midnight. But, Jacob, can you just read to the class what the function says that I asked to sketch next on the handout, which I don't think we'll have the time to do it, but just read it.
4 cosecant.
Whoa, whoa, 4 of these, 4 cosecant.
1/2 x.
Wait, 1/2 x
minus pi over two.
Was the x minus pi over 2 in parentheses?
Yeah, they were in parentheses.
Oh, my lord. Anything else?
No, that's it.
That has a cosecant in it.
Yeah.
So if I go through my little bounding or whatever I gotta do, or transformations, Deborah, when I finally finish up, the graph is gonna resemble the parent. Except this little piece here, I haven't done the graph yet on the handout, it may be over here. After I go through those transformations, this little piece down here could be up here, down here somewhere. Who knows? We haven't done the graph, but it should take a shape, something like this one, the parent graph. It's 5:58. Oh, whoa, 5:58. I'm not gonna have the time to do this right here, the second graph, which I was hoping I would. I'm going to save it until Monday. There's no holiday Monday, please tell me. There's no holiday? If there's another holiday with us being in class, we're having Zoom. Would you guys have joined me on Zoom on Monday?
Yeah.
I wish now I had done it. Okay. Okay, guys, no, we're gonna run out of time, so take your 10-minute break, and then we're gonna start the test.